Let's use what we've learned about momentum and impulse to study injuries in automobile collisions. Now, the main injuries that occur in car crashes are trauma injuries, like brain damage, bone fracture, damage to the skin and internal organs. And it's been experimentally determined that bones fracture when they experience a force of about 90,000 newtons, 90 kilonewtons. And if your head or your brain experiences an acceleration of 150 Gs or 150 times G, 9.8 meters per second squared, for 4 milliseconds, that's fatal 50% of the time. If your head experiences an acceleration of 50 Gs for 60 milliseconds, that's also fatal 50% of the time. Now, when your body collides with something, the dashboard in a car crash, we can talk about the whole body impact pressure. That's the amount of force applied to your body divided by the area over which the force is applied. Pressure equals force divided by area. And if that pressure is below about 1.9 times 10 to the fifth newtons per square meter, you survive. If that pressure is above 3.4 times 10 to the fifth newtons per square meter, that's fatal half the time. So these are kind of loosely experimentally determined quantities. They depends a little bit on the situation, but these are good estimates. So let's analyze a particular collision and see what values we get for the force and acceleration and the pressure on a rider, and then talk about what can be done to improve the safety of a car. So let's have a 75 kilogram passenger in a car and they're not wearing a seatbelt. They are initially traveling at 27 meters per second, which is about 60 miles per hour. And because they're not wearing a seatbelt, when the car crashes and comes to a stop, the person hits the unpadded dashboard and comes to a stop very quickly. So the time of collision is 100th of a second, 0.01 seconds. And V final is 0. Person comes to a stop. It does so very quickly. So let's calculate the force and the acceleration and the pressure that this person experiences. We can do that by using our new tools of momentum and impulse. So let's use the momentum impulse theorem. Remember, that says that the impulse given to an object equals its change in momentum. Impulse is force times time. Change in momentum is mv final minus mv initial. For this situation, v final is 0. Person has come to a stop. So we find that the force, this is like an average force during the collision, mv initial over delta t. And plugging in these numbers, that gives you a value of 2 times 10 to the 5th newtons. This minus sign just means that the force is opposite the direction that the person was going in to begin with. Alright, so this force is big enough to cause serious injury, because 90 kilonewtons is 9 times 10 to the 4 newtons, and so this is much larger than that. This person's bones are going to break. Now, the pressure that they might experience is that force divided by the area of the rider's body that maybe collides with the dashboard. And that's kind of an estimate, depends on the situation, depends on the person. Let's say the area is about half of a square meter. We won't worry about the minus sign, we'll just worry about the magnitudes of these forces and pressures. Well, that is 4 times 10 to the 5th newtons per square meter. And you can see that that is above our 50% fatality threshold. All right, so these numbers are not good. And the acceleration that this person would experience would be change in velocity over time (0 minus 27 meters per second divided by 0.01 seconds. And that gives you a value of 2,700 meters per second squared, which is about 280 Gs. So you're experiencing acceleration 280 times greater than the acceleration of gravity. That's the acceleration of gravity. Imagine accelerating 280 times faster than that. That's not good for your head. Okay, so how can we improve safety of cars? Well, the biggest thing we can do is to increase this value of delta t, lengthen the time of collision. And there are several ways to do that. Seat belts are one way you do that, because instead of coming to a stop by colliding with the windshield or the dashboard, you come to a stop by colliding with the seat belt, which is a little bit stretchier and increases this time of collision, the time it takes to stop you, by quite a bit, a factor of 10 to 100. So if you wear a seatbelt, the stopping time could, for instance, become, say, 0.15 seconds, which is much, much bigger than 0.01 seconds. And if we use that value, then the pressure now becomes, you can try these numbers out on your own if you want, 2.8 times 10 to the 4 newtons per square meter That's a lot less than 4 times 10 to the 5. And the acceleration becomes 18 Gs. And now, wearing the seatbelt and lengthening that collision time means that this accident is now survivable.